After that, we will start our session. I think now there is only 9 participants joined so far.
Evening. We can start the session now.
Okay, so yeah, I can see the participants are less today, so I'm not sure what would be the reason, but Let's stick to the time. We will start the session now and see if other people are joining in. So, yeah, this is just a recap of yesterday's session. So yesterday we have seen that how we are estimating the product limit survival function using Kaplan-Meier method, and how we are going to interpret this survival curve using uh, survival curve derived using the product limit estimates of uh, Kaplan-Meier survival function. Okay, so now today we will be discussing on how we are going to to compare the survival time of two different groups or more than two different groups, and how we are going to see what all are the factors influencing the survival time, or how we can establish whether any covariates are actually influencing the overall survival time of different groups. Okay, so the test we used, very commonly used, is the log rank test. So it is widely used method of comparing two or more survival curves. So if there are two or more groups of individuals, like treatment, control, and a third group like treatment 1, 2, and control group, or something like that. So we will use the log rank test to compare their overall survival uh, functions, like overall survival curves. The log rank test is a non-parametric test, so does not possess any sort of assumptions in testing, which makes no assumptions about the survival distribution. So it does not make any distributional assumptions about survival time. Essentially, the log rank test compares the observed number of events in each group to what would be the expected if the null hypothesis were true, that is, if survival curves were identical. So this is what the log rank test actually compares. And you might have seen this observed and expected kind of things in previous lectures, which is actually tested by a chi-square distribution. At that time, this chi-square distribution is an interesting distribution because it actually plays in the parametric and non-parametric space. So sometimes it is called a semi-parametric distribution. So even though this log rank test is completely non-parametric, we are using the chi-square test to test the significance of this log rank test. I mean, the significance of a difference in survival functions. So the log rank test is approximately distributed as a chi-square test statistics. So that is pretty much about the log rank test. As I told you, it is actually comparing both the survival functions, not the survival time, or not whether the event rate. So we are not comparing any of this. It is actually comparing the survival function of between different groups. So okay, so we will see how we can do a log rank test in SPSS. Uh, so I will just stop share, and I'll just move on to my SPSS screen. So this is the same data you have seen yesterday. Oh, I'm sorry. I need to again stop sharing. So I need to share my screen rather than SPSS. Okay. Okay, so this is the data you have seen yesterday. There are people who have their dead or alive status is represented by 0 or 1, sorry, 1 or 0, and their duration of follow-up is represented by time. And we have three different variables. One is, suppose this group variable is the treatment. 1 represent the treatment group, and 0 represent the non-treatment or control group, and age of that specific participant when he or she entered into the study, and the participant's gender. So we have all these factors, but to illustrate the log rank test, we will consider only group as a factor. So to go to the log rank test, we will use the same method we are using to plot the Kaplan-Meier. So we will come to the Kaplan-Meier, and we will insert time as a time variable, and death status as a death variable and defined the event uh, as one, like one represents the event of interest, in our case, death. And compare factor, you need to go to compare factor and click on log rank test. So we will not be covering Brislow or Tyrone Ware test in our session. This is actually out of scope for our sessions, but log rank test is the one which is very commonly used and very widely accepted test for comparing different survival functions between different groups. Okay, so we will put the group as a factor and leave the strata and label case by variables empty. Strata variable actually is used when we are going to compare survival across, for suppose we wanted to compare survival across male and female separately, then we can actually add gender to the strata. So it will compare the group-wise survival function among males and group-wise survival function among females, so separately. So for the time being, we are not doing that. So we will just put group as a factor, and I'll just check. Okay, we need to get the survival tables and survival plots. We can actually ignore the survival table if we are not reporting. Okay, I'll tell you what to report on survival from the survival table. So okay, let it be there. And mean and median survival. So that's it. Click OK. Click OK. Okay, so starting from the first one, we have total 100 subjects. That is correct. We have 50-50 equal allocation on the treatment and control arm. And we have a number of events, 25 events in both treatment and control arm. We have 25 censored cases also. So since this data is generated by randomly generated by myself, that's why you are getting such a balanced distribution across. So don't try to compare it with anything else. Okay, so and we will go on to group. So this is group 0, and by the end of 5 years, like it is 4.862, suppose it is around 23-ish% of people were alive by the end of 5 years, uh, or by the beginning of 5 years, I'm sorry, by the beginning of 5 years. And in the treatment group, around 43 or 44-ish percentage of people were alive when it reaches to 5 year. Why we see 0.439 here and nothing here? Because nobody died exactly at 5 years. So that's why this time difference is slightly lower to the 5 year. So, and you can see all missing values here because they are censored. So we from this table itself, we can see that there is a higher rate of survival in the treatment group by the end of the 4th year or beginning of 5th year compared to the control group. So here it is only 24%. Then here it is almost double, like slightly lesser than double. And let's see the median or median and mean survival time. We usually report the median survival time. So the median survival time for group 0 is 4.1 years, and for group 1 is 4.5 years of median survival. And we can see this is the log rank test. So we get a chi-square value of 4.3233, which has a significance level of 0.04. At 95% of level of significance, this can be considered as a significant difference between the survival time when we compare the treatment and control group. So this is from the figure itself, we can see that there is a slightly increase in survival when we give the treatment, that is treatment equal to 1, compared to the non-treatment group, which is placebo. So you can see, you can get these numbers actually from here. If you draw a straight line here, it will approximately intercept at 24%, and this will intercept in 44 or 43%, which we see at the beginning. This is the comparison of survival curve. We can actually add and edit these things and put different colors, include confidence intervals, and so many things we can do with that. But that is not the scope of this class. So this is how we can estimate the survival uh, function and compare survival functions between two groups. Here from the survival curve, we can see that there is a 100% survival to certain duration for this patient. So this is a bit of alarming kind of an observation. I will tell you by the end of the session what is this and how we can, what may be a cause reason for this kind of survival functions, and how we can uh, overcome this kind of bias. And but I'll not show you that in SPSS because I'm not sure if that procedure is available in SPSS straightforward. So I will be discussing that bias, but I'll not be showing any practical examples for that. Okay, so that is pretty much about the log rank test. So it shows that there is a significant difference between these survivalship functions, and we have seen a slightly increased survival rate for the treatment group. So now we will go back to our slides. Okay, so that is pretty much about the log rank test. We can compare it with more than two groups also. So the same type of results you will see in more than two groups. So this is a slide from the GLM sessions. We have seen that GLM is actually a common way to specify different classes of models, which is present in regression analysis. So in that GLM, we have seen these models for predicting time to next failure or parts, or such separate models which will handle regression model, which will handle this time to event type of data. So just for a recap, I included this slide in this session. So such models, there are so many different models, but the way very commonly used model is the proportional hazard model, or Cox proportional hazard model, or Cox PH model in survival analysis. Before we dig into the Cox PH model, I'll just give you a brief intro on hazard ratios. So in our previous sessions, day before yesterday, we have seen what is a hazard function. So it is an instantaneous risk, or the force of occurrence of a certain event to a certain cohort or group. So the hazard ratio, what it means that it is actually a ratio from in the intervention or the treatment group towards the control or the non-treatment group. So this hazard ratio will basically it is a ratio of force of certain event happening in treatment group to the force of certain event happening in control groups. So this ratio will give you a single number which can be interpreted, or which will make more sense for comparing the event rate in both the groups. So hazard ratio from these proportions, like we know that both these numbers are positive. So the hazard of risk group is positive, and this one is also positive. So any two positive numbers, if you are doing division, the value can be anywhere between 0 to it will not be 0, but it can be any small number higher than 0 to any small number lesser than infinity. So it can take any value from 0 to infinity. And when hazard ratio is less than 1, so hazard ratio is less than 1, just think about what is happening when hazard ratio is less than 1. Hazard ratio is less than 1 means the numerator value is lesser than the denominator value, which is, in other words, suppose the instantaneous hazard of for the treatment group is 5, and for the control group is 10. So this will give you a value which is less than 1, which is equal to 0.5, which actually represent a half uh, likelihood of occurrence of hazard in the treatment group compared to the control group. And another case is the hazard ratio greater than 1, which means that the treatment or the intervention, whatever we are doing, is increasing the rate of hazard. So don't get confused with this one, because the remission kind of thing, like positive outcomes, if our interest is event of interest is positive outcome, so then there is highly likely that we will see hazard ratio greater than 1. uh, and it actually favors to the treatment group instead of the control group. So which means that it will be, for example, 10 by 5 equal to 2. So whenever the numerator is higher than the denominator, it will give you a value greater than 1. When the numerator is lower than denominator, then it will give you a value of less than 1. And hazard ratio equal to 1 when numerator and denominator are exactly the same. So most of the time, since we are doing a random experiment, the hazard ratios, it is highly unlikely that we get a hazard ratio equal to 1. The hazard ratios will be always less than or greater than 1. And what happen is, like what we will be testing using this hazard ratio is whether the slightly higher or slightly lower hazard ratios, or very high or very low hazard ratios is occurred by a random chance, or is that something which we are expected to see, or we are confident to see in these two groups. So that is how we are testing that is why we are testing the hazard ratios for the significance. So hazard rate may not be constant across the group, but if it is fair to assume that hazard ratios will be same as it measures the ratio at any time. So we can see that the survival curve is not a straight line which run, if we have two groups, it is not a straight line which run parallelly. It is actually a curve which may have a same beginning and but a slightly different growth or slightly different progress. So if we compare the hazard rate at different time points, it may not be equal. Like hazard rate of this curve may not be equal to hazard rate of this curve at any time. So that is actually not possible. If these are equal, most of them will lie on the same line. So this is not possible. But what we can assume, confidently assume, is that the ratio between this hazard rate, like hazard ratio, that this factor which we have discussed now, will be almost similar in throughout the follow-up. So this is actually a very fair assumption to work with, or very fair assumption to proceed with a certain regression analysis with this type of data. So that is the assumption which we are mainly using when we apply a Cox proportional hazard model. We assume that the hazard ratios remains constant throughout the follow-up. And what does this hazard ratio represents? It actually represents a lower or higher risk of experiencing the event during the follow-up. For example, in our case, we have seen, just assume this is our case. So we have seen the hazard ratio is 0.5, or just to be a bit more easier for understanding, because 0.5 is exactly a midpoint. So if we have 2.5 divided by 10, this would be 0.25. So how we are going to interpret this hazard ratio? So if we get a hazard ratio of 0.25, what does it represent? So it is a percentage lower or higher risk of experiencing the event during the follow-up. So suppose if both are having equal equal force of occurrence or equal hazard, both the groups are having equal hazard, then the ratio will be 1, which we assume to be 100%. And from our example, we have seen that the hazard ratio is actually 0.25, which means that the occurrence of event among the treatment group compared to the control group is only 25% instead of 100%. So it is, in other words, it is higher, it is 75% less likely to happen. The event is 75% less likely to happen in the treatment group when we compare it with the control group. So which actually favors to the treatment if we are having an unfavorable outcome like death, or it will favors to the control if we are having a favorable outcome like remission or some occurrence of some good things instead of death or relapse or something like that. Okay, so that is pretty much about hazard models and hazard ratios, and we will see what is a Cox proportional hazard model and how we can link it to the generalized linear model we have seen before. So the Cox-PH model is a regression approach more commonly used in statistical and medical research for investigating the association between survival time of patients and one or more predicted variables. So this is the main use of this Cox proportional hazard model. It actually link the survival time with uh, the covariates available with us. And this is actually really important when we are having multiple covariates. So if you have a single factor covariate like a treatment, we have seen the log rank test and Cox-PH model will result you in the same output. But if we are having more than one variable, it is always preferred that hazard model, Cox proportional hazard model should be followed to model such data. The Cox model is expressed by hazard function denoted by h of t. Hazard function is actually the force of occurrence of that event. Briefly, the hazard function can be interpreted as the risk of dying at time t, or risk of any sort of event of interest happening at time t. It can be estimated as follows. So this is actually the equation of Cox proportional hazard model. Don't worry, I just put this to give you the connection between this one and the linear regression, so that you will understand the generalized linear model. This is also part of a generalized linear model. So it says that the hazard function at time t is equivalent to the base hazard, like common hazard available for both the groups, multiplied by exponent of these different parameters, like x1, x2, x3 are our parameter, our variables of interest. Like this x1 can be gender, x2 can be treatment group, xp can be any sort of other, like diastolic blood pressure, systolic blood pressure, something like that. And beta 1, beta 2, etc. will represent etc. up to beta p will represent the coefficient we estimate for the parameter. So just simply take the natural logarithm of this function. We can see that natural log of h of t is equal to natural log of h naught of t plus, because when it comes to logarithm calculation, it actually replace multiplication by addition, plus natural log of exponent is actually 1. I mean, it's actually cancelled out. So it will start from beta 1 x1 or b1 x1 plus b2 x2 plus etc. So it would be ln of x naught. So we can represent that as a b naught, and ln of ht we can represent it as a y or g dot. So this actually takes a form of a linear regression equation, and so that's why it falls under the generalized linear models. So here in this equation, t represents the survival time, ht represents the hazard function determined by set of p covariates x1, x2, etc., xp. The coefficient beta 1, beta 2, etc., beta p measures the impact or the effect size of this covariate, and the term h naught is called the baseline hazard, is corresponding to the value of hazard if all xi's are equal to 0. The quantity expectation of 0 equals 1, then t and h of t remains as the hazard by remains as that the hazard may vary over time. So Basically, H naught T is actually the baseline hazard, which is actually the event of occurrence, irrelevant whether he falls on group 1 or group 2 or gender, male or female or anything like that. So that is pretty much about the Cox proportional hazard model. And we will now move on to a workout example for Cox pH model. So in our data set, we have three different variables. One is group, age, and gender. So these are the three different variables which we are going to fit the Cox proportional hazard model. But first, I will show you how this is equivalent to the Kaplan-Meier or the log rank test. So in this situation, we put time as time and status as dead, and we define the event as 1. So since we did an analysis already with this data, that's why we cannot define the event again, because it's already been defined as 1. And we put the group as our covariate, only group as our covariate. This is just for an illustration. So we can actually plot separate lines for groups, survival function. Oh, sorry, I don't think we need to do this one to get one plot. This will actually create 2 different plots. So yeah, I hope so. Let's see. And we have to define a group as a categorical variable. Otherwise, it will count it as a number or continuous variable. So I just indicated it as a categorical variable from this side to this side. And plots, save options, confidence interval for expectation of beta. That is true. Just click on that one and I'll explain what does this represents. And group covariates, that's it. We are not doing a stratified analysis. So we can actually put gender in the strata and it will fit 2 different models for male and female. So I'll just click OK. And let's see. So before move on to the Cox expression, just note this is our log rank test we have run, and the significance is 0.40. And this is our Cox proportional hazard model. Yeah, I was supposed to put 2 different lines, so we have to click that one. But yeah, this is a Cox proportional hazard model, and you can see almost similar level of significance for the beta parameter, which is actually 0.582. The exponent of beta is actually 1.790. So we might be in a bit of confusion, like this exponent of beta is actually representing the hazard ratio. So this is a log hazard ratio and this is the hazard ratio. So we might be slightly confused because in the figure it was seen that the group 1 has a lower rate of occurrence, but here when it comes to the hazard ratio, it actually took 1.790. I will tell you where the error was happened. So go to survival, Cox regression, group, categorical, group indicator, reference category we should put as first. So if you put the reference category as last, it is taking the hazard ratio from the last to the first. So it's actually taking the inverse of the hazard ratios we are interested to see. So first means it will give you, okay, so if we take the last option as a reference group, it actually estimating the treatment group as the denominator and control group as the numerator, because we represent 0 for control and 1 for treatment. So if you want to display the result in the same format, we should put control as the reference group. So for that only, we have to choose where does it go? Yeah, we have to choose the first value, that is 0 comes first as a reference value, and continue, and just correct the plot, also separate plot for continue. Okay, and now the, oh sorry, yeah, What happened? This again gives you the same value, which is not correct. Didn't I change that one? See? Oh, it has some issues. It automatically. Okay. So we have to click and change, then it goes there. Okay. So now it gives it makes sense. So it actually reduces the risk. The treatment actually reduces the risk by around 40%, slightly higher than 40%, or reduces the risk of that event by 40%. So we can see the same survival curve, that the treatment group has a slightly higher survival, not slightly, almost a good amount, almost double survival compared to the control group. So this is how we get, how we get the hazard ratios, and we will see how we can include multiple variables in the Cox regression. So we will include all the variables like group, age, and gender. We will go to categorical. Oops, what happened? Something happened. I think I need to close and restart spaces. Let's see. Let's see. This happens sometimes with my spaces after I change my system. I'm sorry about that. So we will check the last loaded data for survival. Okay. Now we will move on to analyze survival, Cox regression. Time is the time variable. Status is death. Define event. 1 represents the death. Covariates are actually all of them. We are not measuring any interaction, just to get the interpretation simpler. Categorical variable is actually group. We take first as a reference group, in group also, and in the gender also. Continue. In this one, we are not so much interested in uh, survival plot, because it would be a bit messy to plot. We can actually plot the overall survival because there are 3 different variables, and we cannot plot the survival with the continuous variables. We can actually plot separate lines for categorical group and gender, but we are not going with that for this example. Then options, confidence interval for expectation of beta. This will give you the 95% confidence interval for the hazard ratios. Continue and click on OK. Okay, so now we have these 3 parameters like group, age, and gender. So these are the beta parameters for this group, age, and gender, but we are interested in hazard ratios. So hazard ratio of a group was slightly slightly lower compared to the previous one, but the significance is not there, because previously we have seen that the significance value is 0.04, but now we can see that this one is not significant when other covariates came into picture. And we can see almost similar relationship between gender and uh, group variables in terms of significance. So another easiest way to see whether a hazard ratio is significant is like if the 95% confidence limit. Hello? Okay. I was listening some other noise, sorry. Uh, if the 95% confidence limit include 1, which means that the hazard ratios what we see is not significant at 95% of level of significance. Yeah, so we can see that none of these factors are actually influential, significantly influencing the hazard function when all these factors are included into the model. So this is how we use Cox proportional hazard model to estimate the hazard ratios and see how different variables are influencing the hazard function. Sorry, the hazard ratios. Okay, so that is pretty much about the Cox proportional hazard models. Am I missing something? No. Now we move on to some of the common errors we face when we do the survival analysis. So most of the time we will be interested to see the survival as a death outcome of interest, like our event of interest most of the time will be death. And age is actually an influential factor for death. So death is actually inevitable, like eventually everybody will die. What we are thinking is like which group of patients are dying faster or dying or more likely to die compared to another group. So if we are not considering age as a factor for survival analysis, then we are doing a mistake. Like we will be including patients with a higher age, and we will end up with uh, more likely to see death in one group. So it is very important that we should match our treatment and control group uh, while doing the survival analysis. Because if there is a unmatched treatment and control group in terms of age, it may not be always age. It can be countries, like controls are selected from a specific ethnicity, or cases are selected from a different ethnicity, or any factor which influencing our event of interest should be matched before we do any experiment. Or we should fit a adjusted model like Cox, like just like the one which we have fitted before. We have seen that in the presence of age and gender, the effect of group is not statistically significant uh, in our situation. And another main issue is the competing risk. So there will be competing risk event present in the data. Like if we are doing in these kind of incidents occur when one type of event actually compete with the other type of event. Like one event happened, it is not possible that the other event will happen. Suppose our event of interest will be a relapse of heart attack, like the duration to the second heart attack. And for some reason, if the patient dies before he experienced the heart attack, and he was still part of our study, but he did not experience the actual event, but it actually he experienced another event which is actually a competing event with the heart attack. Because a person dies means that he will not experience a heart attack again. So that those kind of events are called competing events. So when we define any events other than death, death will always come as a competing event towards that event. So we should rely on competing risk models to illustrate this kind of data. So I'll not be explaining how competing risk models or how we are going to do a competing risk analysis, which is actually a slightly more statistical uh, analysis rather than a simple one, which I have told you, like Cox proportional hazard model. Another issue with competing risk is like if we are not considering the competing risk events, we are highly likely to see that the non-intervention group experience high um, uh, less hazard, because the non-intervention group, most people will be dying and they are not experiencing that event. So the overall event rate will be very low in the non-intervention group compared to the intervention group. So this happens mostly in cancer trials when we compare the relapse with the mortality. So in cancer trials, when we assess the relapse, if mortality is not considered as a competing event. So even though we consider the mortality as a competing event, we may see that non-treatment group will have lesser relapse risk compared to the treatment group, but it was due to the fact that the non-treatment group will die sooner and do not wait for relapse. So these kind of things we should be very careful about when we are planning to do a survival analysis. We should account for all the competing risks available in the situation. Another type of bias is called the immortal bias. Like um, I'll tell you that using. Okay, so I think it is. Mm, okay, when I display this, where is it? Okay, processing. When I display this figure, I told you this is an alarming situation. Like all of them were survived till 1.5 years. So what happens is, like, if we are having an intervention which is actually a certain type of procedure, like surgery or a transplant or any sort of certain type of procedure which we are conducting after certain time. So in this scenario, for the treatment group, for a patient to be included in the treatment group, it is mandatory that he should survive till he receives the treatment. So this is what we called an immortal bias. So this bias, what it does is, like, it actually favors the treatment into unlike so we can see that there are death happening in the control group, but there are no death happening for 1.5 year in the treatment group. But it was only due to the fact that the patient, to be eligible to receive treatment, he should survive till this duration, till he received treatment. So anything happens before his survival is actually not accounted here when we are doing a normal log rank test or normal Cox proportional hazard model. So we should consider there are different approaches to resolve this problem, but most commonly used approach is something called a mental Bayer analysis, which actually consider these patients till this time as a control group, and the patient, when he after he received the treatment, he falls into the treatment group. So the control group, when we are comparing, the control group will have the overall sample size. Like here, if we are doing a mental Bayer analysis, uh, like here, if we are doing a mental pair analysis, the total number in the control group will be 100, and the total number in the treatment group will be 50, and 50 patients from the control group will slowly jump into the treatment group as long as when they receive the treatment. So that is a very common and very accepted method which we use to overcome this sort of immortal bias, which is also a factor which we should be very careful when we are doing a survival analysis. And the last one is longitudinal and time to event models, joint longitudinal and time to event models for longitudinal exposure measurements. So some of the exposure measurements are not constant in time. They are actually longitudinal, like the exposure itself will follow the survival of those patients, like measurements like for example diastolic or systolic blood pressure, like it can vary any time. So taking a baseline measurement as a benchmark and assume that he will follow the same measurement, that is actually a very wrong assumption to follow it. So in such scenarios, if any of this exposure or any of these our variables of interest are followed or longitudinal over time, then we should consider joint longitudinal time to event models, or there are mixture Cox proportional hazard models also. So we should consider suitable models which actually account for this longitudinal exposure measurements. And this is just a cartoon. Our consultant has been mining the data whole day, and the results are quite shocking. According to the data, the sales is always highest when he do some sort of action. So this is actually I just put it as a fun fact that how statistics can be used in a wrong sense. Just like gray hair causes heart attack, like yeah, it's not the gray hair, but the age which plays a role. Okay, so that is pretty much about today's session. So today we have learned how we are comparing different survival curves for different groups, and how we are assessing or evaluating how different variables are influencing the survival time. So any questions?